Thanks. So in the first session, we have spoken about functional programming and Scala, how it works and what are the advantages of using Scala. So today's session, we have planned to discuss on Apache Spark, which is a in-memory big data processing framework, mostly used in popular framework. Mainly, we work with Axion. I mean, we work with Spark in Axion a lot. A couple of customers where we have extensively used Apache Spark and Scala, right? So I'll talk about that. Prior to that, what is important from Scala and which we can hybridly use with Spark that we will discuss. So first thing is to understand the concurrency and parallelism with respect to Spark and Scala. And then we'll discuss about how we can integrate that. So I hope everyone can see my screen, right? So before going to that, let me tell you one concept called side effect. So what is side effect in functional programming? Is that when you write something, if you execute same code more than one time, and if it gives you different output, right? That's called side effect in brief. And anything that interrupt your processing, interrupt your execution style, right? That's called side effect. Mainly side effect is referred when you write concurrent and asynchronous calls. Means you are spawning multiple threads and multiple concurrent input IO, and then you are performing some operation on top of that, and that's affecting, right? That's called side effect. It's not easy to explain side effect when you talk about pragmatically, but we will take some examples and I will explain you that what I mean by side effect on that. So second fundamental principle is to understand referential transparency. So what is referential transparency? Is that when you write when you write a code, right? The concept of purity, the pure function, and the purity where you don't let the complete side effect over there. That's called referential transparency. So if there's a side effect, then you can tell that code is not referential transparent. So generally in functional programming, we want to avoid the side effects. We want to always return the same thing given the same input, but also modifies the external world, right? So we will take some example that what I mean by side effect and how it works. So let me open Scala interpreter and save my screen fully. With you. So this is, let me open Scala here. Now I have got some example for you to put there. So I have created one function called sum, take list of integer, return the integer, and do summation here, right? Now, what I'm doing, I'm calling this function twice, given the list 1, 2, 3, and 1, 2, 3, and taking summation of this function. Now you can see output is 12 here, right? Now I'm doing in different ways. So I have a function called val x is equal to sum list 1, 2, 3, and then I'm doing x plus 1, x, right? This is 12. Now, the question is that which statement has side effect and which statement doesn't have side effect, right? So first one, I mean, side effect, it can be caught by only compiler, right? Now, if you write a code which is not having any side effect, which is referential transparent, you will get same output given by same input. So the code can be reasoned from compiler, okay? That code can be interpreted by compiler and code can tell that whether it has side effect or no. Now this sum of list 1 to 3 and sum of list 1 to 3 in general, right? Now here you call that function once and you get output in immutable variable, and then you just do x plus x, right? It gives you 12. But in this function, which you have sum, now if this and this first code block and second code block has changed, right, you will feel the change in the output here. So anything that which you can control can tell you that whether it has side effect or no. Second example with the future here. Here you will see the output also. Now here we have one for comprehension block in that we are mentioning the future object and we are printing println. We are also printing second time here. Okay, so this is what future object is what it will get executed. So the output would be printing println 2 times, right? So let me run this code. Now you can see the hide there 1 and hide there 2 both are printed here. But what if I get this object entirely in one variable here and print 2 times in the for comprehension, whether this will behave same or no? So here what I'm doing, I'm creating one variable here called printf and putting same thing, whatever you saw here, right? This entire block inside the as an assignment operator to the printf. So you can see here printf. And now technically what you are doing, you are printing this code block inside the code here, right? 2 times. So here we also call same variable 2 times. And rest of the things are pretty much similar, which you can see here. Now, when I execute this, what should happen technically? Hide there should be printed twice, correct? Because we are printing 2 times here, same variable, and it has a println here. But if you see here, it prints once only, right? So that does mean this code has side effect. This code is not referentially transparent. Other definition of telling the same thing is that when you refactor the code, it should behave the same way. But when I'm refactoring this code from example 1 to example 2, sorry, I could see the difference in the output, difference in the behavior, right? So there are data structure which are not functional data structure. Called future is not, future in Scala is not functional data structure. So it can behave differently in different situations, right? Now think like this way, when Apache Spark kind of framework has built with this kind of data structure like Scala, they have to take care about many things, because the user like you and me being developer can write the code in any way, right? There's not one way of writing code, because someone can use if else control structure, then someone want to prefer to use the case statement control structure. So it is not by design that how you code, but it is up to you in programming that how you can refactor your code and write your code. But if any code has a side effect, like it is not referentially transparent, which you see here, then there will be difference in output, and there would be no clue that how we can figure it out something, right? Regardless, we understand that what has side effect and what doesn't have side effect. That's one example here. Now the question is that how we can avoid the side effect. What are the ways to avoid the side effect, and how we can do that? So the only way to avoid the side effect is use pure functional data structure, use pure functions which always return, right? Now think in this way, if you have any function which you call the function like get integer, that is the third-party Java library which you call get integer, and you have no clue in the library that what it does. Probably it gives you integer, that's what you know, but probably it has some database connection calls, and it does database connection call. And when you use that get int in multi-threaded, let's say you spawn up 125 thread, and it calls the same library again and again. And down the line, downstream Java library, which is native Java call, which can cause database lock or deadlock, or it cause the connection timeout, or it cause the number of connection allowed, right, which you don't know. That is side effect for you being a functional programmer, because you don't know that what it does, right? So I mean, unless you know that how you can prevent the side effect of any system in the scope of concurrent and pure asynchronous calls, you will not be able to see that what you can do. Now, the only advantage is that your compiler have guarantees that your code can be reasoned with, and this makes refactoring a walk in park. Means the compilation can be faster, and some of the things which can be optimized in compilation time, so there's no need to optimize that in runtime for the Scala compiler, right? So those are the tricks which you can apply. In brief, again, what is the effect? Anything which you can't just do twice. Writing to a database, right? No one want to do it twice. If something, when you use concurrent and pure asynchronous calls, and by default, let's say your function is called 2 times, then what will happen? You will insert the same data twice, and then you can't really debug that because it's concurrent and asynchronous, right? And let's say if you want to read the input from the standard input, if you read once and if it reads twice, then what will happen? The content will be twice for you. And in some case, if you want to change the state, if you have a flag, turn on, turn off, let's say you are running historical load and incremental load. Now, if that call has called twice, then what will happen? Your flag will change twice. And then that can make the completely workflow being disaster, that now you wanted to actually run incremental run, but it has run full load for you. So those things looks very small, but can cause so many other effect. So, and what are the use case of this functional effect? When you talk about distributed system and system programming at scale, right? Let's say if you want to handle the scale of Flipkart or Walmart or Amazon, right? So at that, where you have a huge amount of scale, you need to do a couple of things at system programming level. That is a dynamic scaling. You want to handle the back pressure. You want to have the dynamic rescaling at some situation. And now you want to have a pool management, that how set pool handle the pool management. Now you want to do resource allocation, right? And think like if that call is called 2 times, what will happen, right? Let's say if there was a failure. Now in concurrent system, you also need to handle the failure. How you can handle the failure. That's called exception handling in the pure asynchronous callback. So I think we are good with this functional aspect of effects. Now I can jump back to how you can prevent that. Yeah, screen was set, sorry. So there are libraries in Scala which you can use, like case effect, which provides you effect handling for you. So now we will use the same example. So what you need to do, you need to go to build.spt, import something called cat score here, called library cat score. And then you can go to the code base and say cats effect IO import, and say import cats implicit. Here I'm saying effect for, and underscore means by default in Scala, default value of something, whatever it comes. You don't have to tell it's integer, this, that. You just tell it's default. Whatever it comes is fine, any. And you say IO println hi there 1, IO println hi there 2. In earlier example, we wrapped the statement with future, but here we are wrapping the statement with IO. IO means IO bound input output concurrent data structure. And then we call this. So let's execute this code. Hi there 1, hi there 2. Now, if you go to cats effect 2, what we are doing, same thing. We have external variable and we are printing here hi there 1, and we are calling the same bit twice here. Now, when you call this, you will see output twice, right? So this is referential transparent code. You refactor the code the way you want, but it will give the same output for the same input, right? It guarantees that. That's the reason this is called referential transparent and pure function. So I think we are good on these fundamentals. If anyone has any question, I would love to answer that. If not, then we will jump back to today's session, okay, Apache Spark and Action with Scala, right? So let me go back to agenda and share my screen. So can everyone see my screen right now?
Yes, Chetan, it's visible.
You can see the presentation called
Yes.
agenda, right?
Yes.
Yeah, so guys, we took last point called why not to use Scala Concurrent Future explicitly as first, because everyone has gone through the what is Scala in first session, right? So I don't want to cover it later stage and get confused that why we are talking about future. But all is about when we talk about distributed computing is to use asynchronous and concurrent calls, right? So it's not about using single machine, single data processing, but you have let's say 5 to 6 nodes and you do computation and processing for the 6th node. Now, when you distribute your workload and tasks to 6th node, how you will be able to control that, whether where it has failed and which it was node, and how you would be able to isolate that environment and get the exception handling, right? That's where you have a future and cat's IO. Yeah, let's go back to Apache Spark. As I said, Apache Spark is the general purpose high-level cluster computing framework, which is a unified engine for processing massive amount of data. And it has APIs for Scala, Java, Python, and R. And it is optimized for general purpose execution graphs. It has got 4 modules. One is Spark SQL, graph processing, machine learning, and streaming application inside the Spark. So you can do 4 kind of data processing parallelly and concurrently with Spark. The primary abstraction in Scala in the Apache Spark is RDD, primary data structure, based on what it works. So RDD is a resilient data structure. It is logical model across distributed storage on clusters. So it gets splitted across different parts. Let's think like 128 MB by default size, and then it is distributed across all the disk and the machine that you have in the cluster. And then on top of that, it applies the function, any function, let's say lambda calculation function or filter. Those functions applies parallelly and get the output by collapse that and combine the output, right? And you can store that data in HDFS or S3 bucket. So what is HDFS? For those people who doesn't know, HDFS is a Hadoop distributed file system, right? So data is replicated by 3 by default. So you have 3 copies of the data in the cluster. RDD is a resilient and immutable. That does mean once you create the RDD, you cannot change the RDD. Second thing, resilient means if you take the RDD input, do something, let's say you do join and then you do filter, and if operation has failed for the one node at the level of filter, it has the ability to recover to original state. And it is compile time type safe. You will be seeing the much more features of Scala what we have discussed in first session in Spark, since Spark is built under the hood with Scala. So it's strongly type inference it provides. It has integer RDD, string RDD, and text RDD, and double binary RDD, which you can create here. It has a lazy evolution. So earlier we discussed that what are the evolution technique in session 2, the part 2, which I said evolutions are lazy, eager, and lazy well, right? I said with that. So Spark performs a lazy evolution by default. It means you try to read your source data like CSV table data with MySQL, and then you join between that, and then you say now perform the filter on top of that, and then you say now write the output to the CSV back to the cluster, right? So what happened that when you say write at that time it will execute entire workflow. In between, if there's an exception, if there's a typecasting error or something, So it will not execute that. It will say, it will throw exception that there is a problem here. Once it validate and qualify entire graph and workflow, which you create as a transformation and the functions, if it is successful, then only it will execute. So it tells that there's no need to pull the data and then your code is failing, right? If your code is working fine, then there's a need to pull the data from the source which you have. So Apache Spark has got two kind of operations. One is transformation and the other is action. Transformations are lazy and it changes the format of the data. If you can see the graph and the picture which I'm presenting here, it was first the leaf and then converted to the, what do you call it, butterfly. At the end, all this transformation happened, right? So it changed from the same format, and every step which you can see in the picture can have a one transformation logically, right? Here, once you do filter, then you do join, then you do union, and then you do accept, and those many things you apply over there. Action is just you, as the picture says, you take action and you do something. So what are the functions and library? It has excellent transformation. There's map, filter, flat map, map partition, set theory, all the data structure of IO that you have zip with index ID. And the actions you have reduce, collect, aggregate, fold, and math statistical actions you have count, take simple, maximum, minimum, sum, histogram, and you can do all statistical distribution here. And this is a Apache Spark core library. You can add the machine learning library, streaming library, and you have much more visibility at the granular level of doing functional operations on top of that. Ultimately, you can save the file wherever you want. So it's not difficult. You have got functions and API for everything which you want to do. Just you need to reason about what you want to do with the data. So the question is that when to use the RDD. When you care about the control of the data structure, when you know how data looks like and you care about low-level API, when you don't care about lots of Lambda functions than DSL, when you don't care about schema, structure of data, because it's kind of unstructured also RDD, and when you don't care about high-level optimization and performance optimization techniques Spark has provided by default. It is very slow for non-JVM languages like Spark and Python and R. When you don't care about inadvertent inefficiencies. Now, what is that? We'll talk after this slide. So inadvertent inefficiencies in RDD is that, let's say you read the RDD and then you apply the filter for the project, which is finance, and then you map it, and then you tell the, can you create the kind of tabular structure where you have number of sprint and number of stories. And then you do reduce by key, which is the operation to reduce the output. And then you say sum underscore plus underscore means you want to sum the sprint total and the number of stories. And then you say filter sprint, which is not e-spatial sprint, right? So why can't you filter it first here when you are filtering the project is finance and then only do reduce operation, because you anyway don't need those records, right? So this is about inadvertent inefficiencies in RDD. In Dataframe, this is by default optimized from Spark, but when you use RDD, you have to take care about this inadvertent inefficiencies, otherwise it will impact the performance. And then you tell take 100 and then you do for each print and stories, and you print number of stories here, right, for each project. So technically speaking, you can bring the data which you need only to the cluster and then process, rather than bringing all the data from the any source system like SQL Server or the MySQL or any other system, where logically, if you think as per your business functionality, you only need those records to process, to compute any KPI or to get any report. So then you will pull only those records by filtering out, by putting the where condition, by joining with other tables. Means you will qualify those records which you need only to the cluster, and then you will process that. So DataSet API in Spark 2.0x is like this. You can read spark.read.json. So I mean, think like that you have very high level API. If you want to pass JSON, you don't have to parse the JSON by telling that this is my Java Pojo. Now you map the Java Pojo with JSON and use Jackson Jersey or any other library to perform that. You just tell spark.read.json and provide the path. you will get automatic output in tabular structure in employee df. Now you want to map it. So we have case class employee name is a string and age is integer. Now you're creating employee ds, output type is the data set employee, and employee data frame as employee. So you are saying that I am mapping the employee df as employee. So you can use Scala native functional aspect of that once you have the type of any object, right? So then you are able to tell here employee ds.filter p.age is greater than 3 here. Now if you change that 3 integer to string, it will fail at compile time, right? Because it is type safe for you to tell the output. And what are the structures are available in Spark? We have data frame, we have data sets. And why data set? Because data set is strongly typing, ability to use powerful lambda functions, and Spark SQL's optimized execution engine, Catalyst and Tungsten. And it can be constructed from JVM objects, and you can change that using functional transformations such as map, filter, and flat map. A data frame is a data set organized into named columns. Means data frame is simply a type alias of the data set of the row. So think like that way, that when you want to have a type alias object from data frame, which is data set of the row, and row is the child object of data frame. So the data frame is built of columns and row. So row is also type in the Spark. So how it works, 3 APIs, different performance at runtime and compile time. For SQL, data frames, and data sets. So the advantage is that if you use the SQL, Spark can be built with SQL. You can just write SQL query and provide Spark.SQL and you can run that. It works. But the side effect is that syntax errors you will get at the runtime. Analysis error you will get at the runtime. Means if you type incorrect column name, like it was employee underscore ID, but you type employee ID, you forgot to put underscore. The output error you will get at the runtime when you run the code at the cluster, you will see the exception of the syntax error, or sorry, you will get analysis error. That's called analysis error. Syntax error also you will get at runtime. In data frame, you will be able to capture the syntax error at the compile time. Analysis error you will also catch at runtime because it's not type safe. But when you use data sets API, you will get both at the compile time. So you will be able to reduce number of runs that you make at the cluster, because in big data you really process, let's say, GBs and TBs of data, right? And let's say TBs of data processing takes 8 hours. And why you need to wait for the 8 hours to catch the exception, right? Otherwise, to make the small change, you need to run a distributed cluster. That takes a long time, and you will be just waiting and spending your nights and weekends to on top of that to figure it out, the exception over there. So analysis can be caught before a job runs on cluster. That's what advantage Datasets API gives you there. The same thing which we explained. Yeah, so if you want to use Dataframe API, same thing which we have done earlier can be done in this way. You just read RDD and say 2DF and map the columns which Dataframe has, project, sprint, and number of stories. And then you say filter, project is equal to finance. And then you say group by sprint because you want to group the output. And you do aggregation, sum, number of stories, and as count. And this all are green color are the column names, right? And limit 100 dot so 100, right? Limit is same SQL operation called limit. So means only showcase the 100 output here. So then you will see the output in such a way, which I can just example, which is here. Now you can, as I said, you can just write SQL query. You can say create or replace temporary view, call audits, and say spark.sql and provide SQL query here, and then say result.so. It will give you the output here. So output is similar, 3 approach, right? But the performance has a different impact. And always remember, in distributed computing, performance does matter, time does matter, right? Because that's the value and that's the money here. And why structure API? This is again same example in different ways, so what you can do here. So how internally it optimizes that based on Catalyst in Spark. So Catalyst is an engine which does the optimization on the output, input and output that you provide. So SQL AST, you have asymmetric tree, and then you have data frame, and then you have data sets. You feed this three type of data structure to unresolved logical plan, and that generate the logical plan, and it has got optimized logical plan, and it has got physical plans that it has built. And now you need to choose the best physical plan, that is cost model, which does the statistical distribution and figure it out from that which model is the best for me to use. And it selects the physical plan, and at the end it will convert to the RDD. Now you might be confused here that why we are talking about all this process, because at the end we get RDD here. But please remember, this RDD is not the same RDD which we were talking about earlier. This is the RDD which is highly optimized. This is the RDD which is the lightweight Java POJO, which can run on JVM top of directly, right? Because again, Spark runs on JVM, so you need to give what JVM loves, right? So JVM loves Java objects, and you will give Java object here at the end of RDD. As RDD is a primarily abstract and fundamental data structure in Spark, so you need to convert everything to RDD at the end. So data frame optimization, as we said that, let's say in this example, you read event file, employee table, and then you join, and then you filter. That's called logical plan. In a physical plan, what happens that it scans the employee. This is the example. We are joining employee with events on employee ID and event ID. We are filtering event date greater than 2015 1st January 1st, right? And then you scan the employee, you filter that, and then you join here. And physical plan with the predicate pushdown and column pruning, right? So in physical plan, that when it selects, it optimizes scan here, because it knows that it has to only pull the events which is greater than 1st January 2015, and optimize scan for the employee. Okay, that for the employee table, what you need to do, if there any constraint which can be pulled out, no, nothing, then it is just optimized, and then you join both together, right? So let's say if you have other filter on employee, that employee belongs to the finance department, then it should pull filter here, and then it gives you the output over there, right? I think this is not needed here. So I mean, ultimately you can case the RDDs and data set in memory. Once you scan that, the advantage is that multiple times you apply the action on top of that, it don't have to execute the same day again. It can pull the output from that memory which you have cached over there, right? So you can just simply say rdd.cache or dataframe.cache. It will cache to the memory. So data sets are faster in terms of serialization and deserialization. Now, serialization and deserialization is one of the technique which you can see here, Java, Cryo, and encoders. So the faster is by default encoders in dataset compared to Java and Cryo. But Cryo is much more faster than Java serialization also. Now, this is all about theory, that how it works and what is fundamental, how you can write your code, right? But how you understand when you execute, right? Reasoning about that, and the internal kind of heuristic about how you understand output, how it behaves when it behaves, how you can kind of interpret the behavior here, right? So what are the key points that you need to remember? The key points are executors, core, container, stage, job, and task. So this terminology is very important to understand, that in Spark internals, what is the job inside the Spark job? Each transformation and the action mapping that you do in Spark would create a separate job in that. Stage is what? A set of tasks in each job which can run parallel using thread pool executor. Task is the lowest level of concurrent and parallel execution unit. Each stage is split into number of partition tasks. So the formula is that number of tasks is equal to stage into number of partitions in the stage. So let's say you have one stage. Let's say you have 3 stages for one job, and then you have each stage has, let's say, 20 partitions. So the output will be how much? 3 into 20 is what you will count there. So 60 is number of tasks that you have. How it looks pictorially, right? So it looks, when you represent in Spark UI, this is kind of pictorial representation of the job. These are the job. You can see job ID 124, 113, right? And it does some transformation action which we have just spoken last. stages. It's a group of stage. You run the stage called thread pool executor. It has some number of jobs inside that. And how you can visualize stage here, you can see here executors are added, executors are gone. So what is executor by default? By the way, executor means the one container running on the yarn. So executor, you can think, is a virtual JVM. One virtual JVM on the cluster is executor. So you can run your code on top of that. And executor has got some amount of cores and memory allocated with help of that. It's runtime. It can be added, it can be removed, right? Which you can see added, and removed there. So when needed, it can come up virtually, it can go away. Task, which you can see here, tasks are this all task which does success or failure. It does all pulling of data, it writing of the data, whatsoever it is, right? So Spark on the yarn. Yarn is an orchestration tool where you can orchestrate multiple jobs, means who can handle the multiple jobs. You submit 50 jobs, then how you will be able to see what is the behavior of the 50 jobs, which job is taking how much memory, and which job is running, which job is failing, which job is accepted mode and yet to start. Those things, for that you will use the yarn, and then yarn has a UI where you can check and visualize your intentions over there. So yarn.scheduler minimum allocation virtual cores is what you can see how many minimum virtual core you want to allocate per container, which is executor. And then you have how much maximum allocation you want to do for the virtual cores, which is 6 by default here in our example. And then you have allocation of the memory. This is 4 GB, and allocation maximum is 28 GB, right? And then how you can decide that, let's say you have resources called 54 GB of the memory yarn is allocated. So how you can decide that how many containers, means how many jobs you can run. One Spark job is one container, think like that way. So you have 54 GB of memory divided by minimum allocation of the memory is 4096. If you divide that, you will see that 13 job is what you can run at a time at maximum, right? Even you allocate minimum memory, the maximum number of jobs which you can run on the cluster given this configuration is 13. So this helps you to reason that how you can scale your code, how many jobs you can run, and how you can proceed further. So if you understand this rigorously, that what would be the combination and permutation here, you would be able to come up with your workflow. How you can check number of cores, you can go to Linux and say ls CPU, it will tell you the number of cores are how much. In this our case, it is 8 CPU. So CPU and cores are same. For those people who doesn't understand the terminology, CPU is equal to core. And how you can tune the yarn here, let's say you have a minimum, whatever we spoke, all the configuration in earlier slide, you can just change here and update that from the UI. Everything, UI, Ambari UI can help you. There's an interface on yarn, Ambari Hortonworks, where you can just change the drag and drop your knobs by turning on and off and understand that how it can be tuned. So once we tune here, let's say I'm changing 6 to 8 for the allocation virtual cores. You can see virtual core 32 here. Once I change here, you will see the virtual core is 52, right? So you would don't just think that whatever you can see on yarn is the fixed amount of configuration. No, you can change that to the maximum upper limit of the hardware that you have. If you allocate more memory than what it has, it will give you exception that you have requested more than what is being configured, right? Maximum configuration. So you can't go above the limit of a upper layer or upper bound and try to, over allocate resources on the Spark job. No, you can't do that. You have Spark scheduler from FIFO to FAIR. FIFO runs the all tasks on sequential mode inside the Spark job. But if you want to have FAIR, if you want to change the execution model, you can change to FAIR, and you can actually combine this with the future or CATS IO to tune that. This is case study, but how much time we have, Neelam? Can someone tell how much time we have?
I think 15 minutes.
Okay, thanks. I think I'm on time. Yeah. So this is all great. We understood things inside that, how terminology works, and now let's talk about real examples, right? So I will see that how much I can cover, and if I'm not able to cover, I will record the session after this call, and then would be able to share with you whatever has left. Since each session that we have are kind of one subject area, and technically it cannot be covered in 1 hour, but I'll see that how much better I can help you. So this case study, we had 14 years of old written ETL platform and 2 SQL largest file. Each file had around 20,000 lines of code, and we wanted to transform that, re-engineer that project to Scala, Spark, and Airflow-based highly scalable non-blocking implementation. So how we have done that, so I'll talk brief on that. We have used Scala and Python, data access libraries, Apache Spark, and Spark Core, Spark SQL, Scoop, and data processing engine, Spark, Airflow as an orchestration tool. For the cluster management, we have used Yarn. For the storage, we have used HDFS Parquet, and Hadoop distribution, we have used Hortonworks. This is high-level architecture. We pull the data from online transition processing system. We have shadow data source there. We have parallelism and concurrency-based system with Airflow, and then we have Apache Spark and Scoop. We have Spark SQL. We have HDFS to pull the Parquet, and then we do bulk load to customer-specific reporting DB here, right? Let me see. Yeah, we're great. So how it looks. So when we orchestrate with Airflow, it looks like that. We have many jobs running on the graph, and this is directed acyclic graph, but not the Spark directed acyclic graph. This is the directed acyclic graph of the Airflow. All the gray color sub-data there, it has again other directed acyclic graph, and each Spark job has own directed acyclic graph, right? So everything is a lazy, immutable, and runs based on whatever needed. You can avoid the join. In this example, let's say you have one data frame upfill amount, and other data frame you have something else old, and then you join both of that, and then you do processing, right? Now what you can do that, you can have a one join and do everything over there, so you can avoid the one more extra join. Like this way, you have joined that and you do all aggregation in one area, right? Such kind of a manual kind of heuristic based joins, you can tune that based on your functionality, right? Now here Spark can't help you. If you write your code in incorrect approach way based on your, without tuning your functionality, Spark wouldn't be able to help you here. I mean, you need to see manually and then write the code accordingly with Spark loves, right? It's two-way. If you give the better thing and thoughts to Spark, it will give you same better positive thoughts to you back. If you give a garbage in, it will give you garbage out. So it's all about developer to write the code which Spark loves, right? Spark tells that this is my standard, this is my process. If you write the code in this way, I will love that, and then you have to write the code according to that checklist. Size of the data frame, number of records in data frame, you have to compare to primary data frame, right? So you can see here we have many joins here, at least 123 joins in one data frame. So how you can do that? You can see broadcast. Broadcast is something which saves the data to across all the data node, and then it computes up then doing more shuffle. So whenever you join your data frame on left side, you can only have the computed column and the primary key. So when you join, you just have to shuffle less amount of data on the cluster. So less number of shuffle you do and more computation you achieve, that's where you will have a much more advantage over there. So parallel read from JDBC, challenges and best practices. So we have a code. Let's say what happens when you run this code, sample df, it pulls the data, and what's the impact on database engine side. So when you run this code, you will see here that in SQL Server, it creates the connection. It tells you running or suspended, right? So this runs on single node, I mean single executor, single thread, on single CPU. Now, when you want to parallelize that, want to pull the data parallelly and collapse the output in that, how you can do this is SQL query to get the start time, end time of the connection, which you establish at the SQL Server. And then you have got custom employee split. This is a method which you wrote, which tells you that how you can get lower bound and upper bound in JDBC and give that. So first example tells you that you call the method and you give the table name and the on column, and it gives you two value, upper bound and lower bound in a list. So you can say upper bound is the head of the list. In Scala, list head means first value, and the 1 is what it gives you second value of the list. 0 is the first anyway, right? So the function, what it does, when you pass any table or the query, it will get the minimum value and the maximum value of the primary key and return you in the form of list here. So then you can just give that back to your employee, the callback, where you want to have a first and second value over there, upper bound and lower bound. When you want to do with the table, you just pass the table. It does the same thing here. And if you have the predicate, like if you where close, right, you can pass the where close here. Otherwise, by default, 1 is equal to 1. It will take and give you the upper bound and lower bound for you. So you can use that also there. So now you can see after doing that, you have multiple connections established at SQL Server, and it is pulling the data parallelly here, right? So if you have a single connection, you pull data slowly, slowly, slowly. It takes time. If you establish and multiple connection, parallel connection at the SQL Server side also, and pull data parallelly from SQL Server, then it is faster, right? So that's how you can change your approach in the code base. That's fair. That's fair enough. We spoke on read. Now how we can parallelize the write, or how we can tune the write. When you use JDBC write, some of the extent it used number of connections that your partition that you have for the data frame, but it still use row by row. Read and write in JDBC are row by row, one row, second row, third row, like that. So if you want to create the batch like 1 lakh, 2 lakhs, or 100K, 200K, and the suit just write stream back to the table, how you can do that? You have to use called Azure Bulk Load API, where you provide the bulk load batch size, let's say 200K here, timeout 1800, and you do table lock. When you do table lock, it can just spawn one stream and write back everything to the table. Right, this is an example how you can do that. Now we'll talk about optimization strategy for the joins. Spark mainly has 2 types of join. There are 6 types of joins in Spark, but mainly default is SortMergeJoin, other is BroadcastHashJoin. So join selection and execution planning strategy, which uses the variable called spark.sql.auto-broadcast-join threshold, which is property by default 10 megabyte to control the size of data set before broadcasting it to all worker nodes when performing a join. So how you can see that? You can say spark.configuration.get this variable to integer. You will see it's a 10 here. So then you can go to Spark df query execution, logical numbered tree string, and then you can also see the query plan by saying sample df.explain. Now partitioning plays a very key role in Spark, number of partition and number of buckets here, right? So partition is like splitting the data frame in different chunks and then doing processing over there, right? So if you want to boost the parallelism, you have to use the partition, and by increasing the number of partition on joins to get the same key joins faster, you can do that. So you can reduce number of partitions without shuffling, where repartition does equal data shuffling across the cluster. If you want to reduce, you can say call as 10. If you want to have, in case of bulk load API, parameter is 1500, let's say, base size, and means data frame has 10 partitions, and each partition will write 2500 records parallelly, right? So this can reduce the impact on network communication, file IO, network IO, bandwidth IO, all the CPU IO bound, and that you can tune that. I think we spoke on this. Now you see this in example, before optimization, you have suffering 97 MB. Here, that's fine. Some cases you see 6.7 GB exchange happening. So 6.7 GB is very high. This is, you can tune that. And then you can see 41.1 GB here exchange, 44.0 GB, 44, yeah. And then once you tune the job, you will see the difference in 5.5 GB, fine. Now, this example, after tuning, you see 186.5 MB shuffle. That's still okay compared to 44 GB, right? So you can go to DAG and see the visualization, like where the action is happening and where it can be tuned, right? What to do when Spark default sort doesn't work? What are the alternatives? Sort in Spark is based on the partition, and the partition suffers and data get again ruined, right? So if you do default sort will not work, you can use collect list from the Dataframe, and then you can say create UDF and provide sort by lowercase, then comma, and then you can use the same function here at aggregation level. This will work. And drop duplicate doesn't result consistency. What is alternative, right? So as far as drop duplicates is a concern, it is just an alias of distinct for you. It doesn't say that it will guarantee that it will return the first record even if you sort the data frame. So if you want to, in your case, if you want to pull the first record, right, then you can use the window operation by and use some rank function like row number over the partition that you have window. And then you can say, I want a row number which is 1 and drop everything else, right? So you can use the alternative as such. And can we use Scala Concurrent Future explicitly within Spark? Yeah, you can use that, but it has also side effect that we spoke with difference between cats IO and Future earlier, right? I'll talk much more on that front, but this is the way you can do. You can create a method, combine the transformation in one method, return the future, and at the end you can just say zip the future A and B, means combine both, and then you say right for each. Now here, what's happening until all the futures are executed, right? You don't know the error, because are you stopping if future 1 failed? You are stopping the entire code? No, because you're waiting for other future to complete also, because that's where you are combining both that. And on top of that, you are doing the blocking call saying that you wait for that, because your code is written in such a way that you need to wait for others. But technically, if first future fails, you can fail your Spark job and don't do that. But Future doesn't allow that, because it overrides the exceptions, it overrides the status of other futures together. There's no way to do that in Scala. That's where you can use the gets IO over there. 1 minute. I have one example to tell on Future is that so couple of things that when you work with Future is the performance, is the cancellation and timeout, effect combination, how you can do that, resource safety, and the concurrency, how you can handle, right? The problem is that there's no method on Future to restart that. You can't do that. And also you get exception overwritten on different future to one future, right? And then that's where there's a worry that how you can handle that. What are things you can do that with the Future, and when it overrides the exception, you can't get exception of the first future on second future, right? Because you don't have concurrency primitives available with Future that you can handle that. So, I mean, it's not only one way. Future runs actions by default eagerly, and which is there. It's an incompetent solution, but it has tons of problem with it. When you think about IO monad, it runs action eagerly by default. So you can construct a future around wrapped within println, which we saw just now. It start printing, but see, the future kickstart the time you create. So the example, let me save that. So if you create the future here, this code block will not wait for anything. It kickstart the time you create, right? So there's no dependency. It is just a eager execution model, right? It will not wait for you. Now, let's say you have println and you have other computation a plus b plus c, and then c you print in this. Before a plus b plus c get computed, the future will println, right? So in some of the cases, high level, you might face trouble like that. It also memoizes the result, so we can't run multiple times. It gives the result to the memory, so you can't run the multiple times. Also, it leaks the memory. So future can hold the memory for X amount of time and make your constructed object unpleasant. But this eager execution running things really problem. That's a fundamental issue which prevents you to use IO monad, and we can see it from the example that we have discussed, right? So yeah, I mean, that's it. Any questions?